In a photovoltaic, the light comes from the top surface. So for a thick semiconductor, there will be more photogenerated electrons and holes near the surface and fewer deeper in. This is not only because the light intensity decreases as it is absorbed in the semiconductor, but also because the photogenerated electron and hole pairs diffuse beyond the illuminated region, but may not get to the other side before recombining. Their diffusion is limited by a diffusion length. In this section, we will discuss the continuity equation and use it to solve this example problem to derive the diffusion length of electrons and holes in a semiconductor. The continuity equation is essentially an accounting of particles in a system, here either electrons or holes. For example, holes in a particular region might be photogenerated or recombined with electrons, but also be flowing into or out of the region. The total number of holes should account for all these effects. For example, let's consider how the concentration of holes P might change in space x and time t, so P is a function of x and t. Let's think of ways the concentration of P, the number of holes per volume, at a given point x might increase or decrease with time t. What would make dP dt positive? One way would be to have more holes flowing into the region than flowing out. Here we have 3 holes flowing in and only 2 holes flowing out, so the number of holes in the region must be increasing by 1. Having the flow of holes change entering at x and leaving at x plus delta x means the spatial derivative dj dx is non-zero. In our example, j is decreasing as a function of x, meaning dj dx is negative, so a minus sign is needed to make the concentration increase. Since current flux J is typically the charge current in coulombs per area, to convert that number to holes, we need to divide by the charge of a hole, E. Now we have the most essential part of the continuity equation that you will find in other fields of physics, such as fluid dynamics, that a change in density is something associated with the gradient of the flux of that same thing. Notice that the x derivative of the particle flux makes the units the same on both sides. Now we also need to add the source and sink terms because of the photogeneration and recombination. We saw before that the recombination rate dP dt is equal to the density of holes greater than the equilibrium value, delta P, divided by the recombination lifetime, tau. The minus sign is needed to make the concentration decrease when there are excess holes when delta P is positive. Then we should also add the generation rate when there is photoexcitation or some other external process creating holes. Note that the generation rate G should be the rate of holes generated per unit volume, which should be proportional to the light intensity. For most of the problems we will consider, we will make approximations that simplify the continuity equation. For example, we will approximate the flow of electrons to be one-dimensional problems where we can have just the x derivative. In 3 dimensions, the spatial derivative of J is actually a divergence del dot J in the continuity equation. For example, when we discussed the recombination of holes after illumination, we said the rate of change in the hole concentration is negative delta P over tau. When the light is off, the generation term G is 0. Also, we were approximating a homogeneous illumination, so there should be no charge flow in any direction, so no divergence or gradient of J. Thus, the equation we were using was the continuity equation with these 2 terms being 0. Under steady-state illumination, we said that G exactly compensated the recombination rate delta P over tau. This was also the continuity equation where, by steady state, we mean that the number of holes is no longer changing with time, or dP dt equals 0, leaving us just the generation and recombination terms in the continuity equation. These values are effectively measured in a photoconductor where the conductivity equals Ne mu for the electrons plus Pe mu for the holes. Imagine that you have an illuminated semiconductor creating electron and hole pairs, and you want to know how far these photoexcited charge carriers get into the semiconductor. For now, let's approximate the light as all being absorbed near the surface. Again, since it is simpler to follow the minority carriers, let's consider the semiconductor to be N-type, and we will be considering the hole concentration in an N-type material, P sub n. Let's say that the illumination produces a hole concentration increase of delta P sub n at the surface x equals 0, and we want to know how it changes as a function of x, considering that some of the holes should diffuse into the semiconductor. Using the drift diffusion equation, we will approximate that there is no drift current because we don't expect an electric field, at least for now, and all we have is the diffusion current. Here we use a minus sign because we expect a positive current in the x direction, where P is decreasing with x, or dP dx is negative. For the continuity equation, we are considering the steady state where dP dt equals 0, and approximating G equals 0 because there is no further photoexcitation beyond the surface. This gives a relationship between the recombination rate and the gradient of J. Combining the two equations gives the second derivative of P should be proportional to P. Considering that P is the constant equilibrium value plus delta P, the solution is an exponential where the characteristic length is square root of d times tau. Thus, we have shown that the photoexcited charge carriers diffuse in a semiconductor with a profile like an exponential decay, where the characteristic diffusion length is the square root of the diffusion coefficient times the recombination lifetime. In hindsight, this should not be too surprising, as we know diffusion length is the square root of d times time, and the excess charge carriers only have a lifetime tau. Note that because of the Einstein relation, d times tau is related to mobility times tau, which are both material properties. Semiconductors with large mu-tau products are needed to make efficient devices that utilize minority charge carriers, such as solar cells and microelectronics. Considering that the electron and holes produced have different diffusion lengths from different d-tau products, then the charges won't entirely balance, with one charge carrier diffusing further than the other. For this example, the excess electrons are relatively less noticeable at the illuminated end compared to the equilibrium concentration, but persist further away than the holes due to a longer diffusion length. This will create a charge imbalance that causes an internal electric field and therefore a small drift current. The drift current for electrons will oppose the diffusion current for electrons. The next level of approximation then includes both drift and diffusion, as well as continuity equations for both species. A good first approximation ignores some complicating details to give the correct qualitative trend. Here, the concentration profile due to diffusion only, and diffusion current. This can be used to approximate the compensating drift current to get a more precise answer by iterating more levels of complexity. Such approximations are extremely useful for debugging numerical solutions to complex problems.